Alright. So what now we have two waves or two kind of wave in our lesson. One is electron and one is photon. Although we all try to describe these two stuff with a wave equation, but these two have some fundamental difference in the laser waveguide. Let's try. Some people can give a good guess. I think there will be two good guess of this question. 对吗？这就是其中一个答案。然后另外一个答案是他们处理的 statistic 不一样，一个用 Fermi Dirac， 一个用 Einstein， 但无所谓，这个定义就是对，他们的波长不一样。Although they are all treated the wave, but their wavelengths differed really much. For a semiconductor laser diode, no matter its invisible light or IR, its scale is in hundreds of nanometers. For example, for visible eye, probably 400 nanometers. For the iPhone you have, the wavelength is 980 nanometers. But for electron, the wavelengths, fundamental wavelengths, is in few nanometers. So the scale could be 100 times difference. So let's consider a double heterostructure. And we treat this as a waveguide. If it is a good waveguide for photon, then you need a sufficient V. The sufficient V is either the refractive index is very different or the distance is large enough. Anyway, that means the wavelengths, the waveguide structure should be in the level of the photon wavelengths, probably 100 nanometer, around 100 nanometer. But such a structure is too wide for your electron. It makes a very poor electrical confinement. You need to do very, very hard to make your Fermi level approaching to the EC over EV in order to make a population inversion, like we discussed 2 weeks before. Anyway, so we have, if you only want one confinement structure to simultaneously to combine the electron and the light, it is impossible. But at the beginning, people don't want to try difficult or complex structure due to the capability of processing. 50 years ago, they only do DH laser because it's better than none. Yeah, better than no confinement structure. So after the beginning 10 years of the development, people start trying to do another structure called the separate confinement heterostructure. That is, I'm not trying to compromise the wavelength difference between the electron and the photon. I just do it both. 小孩子才做选择。Okay. So you wanted the confinement structure for the both sides. So you have few quantum wells in the middle, and a larger scale wavelength a larger scale structure in the scale of photon. And the EC and the energy profile like this. The active region has the lowest energy. The guiding layer, the one wider than the active region, has a larger energy. So the electron, you point your electron and the hole that will be concentrated in the quantum well which emitted light. But we decided another additional layer that this guiding layer doesn't appear in LED. Yeah, but because you have a different material here and we have a different energy difference, that also gives you the different refractive index difference here. So you have another confinement structure called the guiding layer. So it is a good approach if your processing allows to do a several confinement structure simultaneously for your electron and the photons. Then, now how to calculate its confinement factor? In a DH structure, the whole guiding layer is contributing jet. So the confinement structure usually will count for all the anti layers here. But for several confinement heterostructure, only the few quantum wells is the region providing material optical gap to your material. So the confinement factor will be reduced to. It's also the division of two integrals, but the numerator only integrates the region, which is quantum wells. So the confinement factor compared to SCH looks much smaller. The confinement factor of SCH probably could be 0.2, 0.3, or even 40%, something like that. But for the confinement structure of a quantum well, the confinement factor is usually 3% or 2% because the weak thickness or your field is low. But the high concentration might compensate the sacrifice of confinement structure. Since you only need a much less carrier injection to fulfill, to let the Fermi level surpassing the ground state in order to get the population inversion. So if you have a good design and a mature processing, the SCH is the proven structure for the current semiconductor laser diode. Even till now, all the semiconductor laser diode you can buy in the market, are all several confinement heterostructure. So now we have the confinement factor only in one direction. But in the real device, we will have some more complex structure in order to confine the light at both directions. One of the most common the case is the ridge waveguide. We can consider a structure like this. It is just like a ridge. Ridge is woods and base. Okay. So now we are facing the laser diode at our front. We are not looking at the side. So if this is a laser diode, the structure we draw is we look it from here. And we are trying to our view to look at our laser from this side. So it may look like this. So we have SCH like this. This is your NQW, multiple quantum well, and have a guiding layer GL, and a cladding layer CL, and a different layer. So this is one layer, and then the other layer, something like this. And the growth is in the direction. However, we want the light to be focused in the center. So we intentionally etch the material at the side to keep a finite width at the top. So the light can be squeezed in the lateral direction. So in this case, now you have some good simulation software. So you just do the Maxwell equation brutally, with this good computer. But at the beginning, people want to know how good the confinement factor is. If you want to take a 2D case, they will approximate the whole material as a rectangular waveguide. That means we took this small part as the AP region and do 风格。So it makes such a structure and simplified like this. And this is the eddy region. And we give it different Okay, so you need an here. And we still want to make a confinement factor. Although calculating with this method doesn't really, it's not very useful now. I think it will be better. But I think we need to give you some insight with reasonable calculation. We still need to do that. So how do we do that? You consider we also have effective mass propagating outside the plane. Now this is the one guy outside the plane. Then we also have projected Ks and the projected Ky. And effective and the K, this is the Km2 from the diagonal of such rectangular. So that would be Kx squared equal to Ky squared plus beta squared. And the beta is K0 times NEFF. So we can argue this term first. So if we assume this term doesn't exist, then this is the case of the vertical confinement with the slave wave guide. So we can take this part of since this is the eddy region. This is the eddy region. So N1 how should I say that? Okay. N11, Ni1, Ni2, Ni3, N21, N22, N23, N31, N32, Okay, this is 3x3 division of the effective index. We approximate our region laser like this. And if you doesn't consider the Ky first, so we only see this part, then we can calculate EFF with the given procedure in the next page. Surely you can also do the same thing with this part and this part. So you will with this three number, you will get a NIEFF and another N3EFF. Then consider this as another waveguide to obtain the really effective index. Alright. Then, along with this one, we can already get an optical mode like this, right? So with this one, we already got a confinement factor around the eddy region. And with these three new effective mass, we can get another waveguide in the lateral direction. So this also give you a gamma y, the confinement factor in the lateral direction. Then the overall confinement factor of the two-dimensional plane goes to gamma x, gamma y. It is very good approximation. with some mathematical decency. And mathematically it's reasonable. It's not trying to being lazy and do whatever we want. It is a reasonable approach. So let's try a real example. Okay, so let's consider a gas-outgas pH structure. And the PR gas is etched and deposited with some dielectric, with a relatively low, much lower refracting index, because that's what really happens. The refracting index of 3.5 is actually pretty high. So for common dielectric, the dielectric constant is usually much smaller. The refracting mass is much smaller than gallium arsenide. Alright, so the full gallium arsenide is such a wavelength 3.593. And the effective mass of the refracting index of the outgas and at both sides are all 3.495. It should be lower, or you cannot form a waveguide. Alright, so we have also formed a 3x3 index profile now. So let's start with the central region. So the B is 3.593 squared minus 3.495 squared. Take the square root. And the K0 is 2 pi over lambda. So because the laser now we have is the 900 nanometer laser. So the refracting index is 2 pi over 900. And the D here is 300 nanometer. Alright, so you just, calculate that with the calculator. We go, okay, the refracting index is 1.745. It's a rather small value, but that's okay. So we can, then we have B, then the approximator to obtain B. Then you obtain B to be 0.302. Alright. So the effective mass index to B is also defined as this. So its effective mass index, the effective index in the central region is just put it to this side and approximate one squared and take the square root. Alright. So it turns out 3.534. Okay. So we get its gamma index by substituting the B here and the B here. It turns out normal or the transverse effective index to be 0.607 0.607相当高的一个数字。Alright. Okay, then we repeat that with the side region again. The procedure is the same. But so I said that the page, the interval is wrong. We need to take the higher value. So the V is still the same. It's still 1.745. And since because this is a symmetric waveguide, we have a value for the A, and it is calculated by the same one. This is the larger difference, 3.45. Okay, 3.497 squared divided by 2.218 squared divided into the smaller difference. Okay, the result is around 10. Okay, we have we did around 10. Then, so the number is exact. I intentionally make the number be around 10. So if we see the curve with A to be 10 and the B to be 1.75. So B is around 1.75 and the A is equal to 10. So the number is around 0.1. Alright. So according to the figure, B is around 0.1. then we can calculate the effective index at the side to be 3.505. Alright? So you have the central one to be 3.534 and the edge one is 3.505. Then repeat the whole process again. You get a V because the ridge width is 5 micron. 5 micron is already pretty tight for conventional contact lithography. So usually you cannot have a 300 nanometer wide. This is already a semiconductor level process, which doesn't happen in the common semiconductor laser diode. So 5 micron or 2 micron at the most is already pretty narrow. And we see that because you have a pretty wide V for the common ridge wave laser, so the V is usually is much larger than the vertical confinement. So it turns out the gamma Y, the lateral confinement is usually pretty large. However, if today we want to make a very narrow ridge laser, if we want to make a laser ridge small in order to suppress the high order mode, I want it to be single mode. So I intentionally make a ridge pretty small. For example, probably I want to make it 1.5 micron. What happens? So according to the number, definitely you will get a smaller V. You get a smaller V, you get a smaller gamma Y. Your confinement factor will be sacrificed. With the sacrificed confinement factor, your threshold current, your threshold gap will also be sacrificed. So this will explain why a single mode laser, if after finish that, probably you can try to read some numbers of the laser you can buy on the eBay or Google. Actually now you can buy semiconductor laser diode from the internet. And if you see the ridge wave, the laser, if you say it is a single mode laser, to make a single mode, you need to make a narrow ridge to confine the optical mode with only one solution. So with a very narrow ridge, that will give you actually rather weak, WEAK, weak optical confinement in the lateral direction. So the threshold current density is usually higher. Well, that's a pretty simple explanation of it. Okay, so back to this problem. Now we have the vertical confinement factor is 0.607 and the lateral confinement factor almost 1. So we got yield a final confinement factor still around 0.602. This is a very good practice for it to test you whether did you learn something from that. So